Actually, you can probably guess why the early pioneers would assume a second hyperbolic function could be a solution to this master equation. Master equation is here. You see, it contains just two parts. Second order time derivative part and some constant times the original a of t. Also the third part, absolute square of the solution times the solution itself. Okay? So if the solution is second hyperbolic, what would happen? You have to perform this one, second order time derivative for second hyperbolic function. And according to the table in calculus, you know sec double prime equals sec itself minus 2 times sec cubic. So second order derivative simply gives you the function itself as well as its cubic. Okay. Only two possibilities. Then the first term is finished, right? How about the second term? G minus L is a constant times a of t, but a of t is such function. Okay? So you still have such function only. The third one is gamma constant times absolute square of the solution, which is sec square, times the solution itself, which is sec. So sec square times sec, you have sec cubic. So it becomes a set， 这是一个封闭集合，对不对？二阶微分给你函数本身跟它的这个立方项，常数乘自己，那当然就是函数本身。函数本身的平方再乘函数自己，又得到函数的立方项。所以你发现呢，你如果假设 sec 是你的 solution， 你发现最后你做完这些计算之后 ，you have only two functionals. One is sec function itself. The other is sec cubic. Of course, with different leading coefficients. Okay, so you will have something like this. After substitution, you got this sec function with a leading coefficient. Say it's symbolized as big A. Of course, it's a function of two unknown constants, A0 and TP, some function of A. Okay. Sec cubic has its own coefficient, big B. It's also a function of A0 and TP. And the summation is equal to 0, no matter what A0 and TP is. Okay? So this equation means you have two algebraic equations. One is big A equals 0. The other is big B equals 0. 这两个系应该说 sec 跟 sec cubic 做 maybe like 线性组合 linear combination equals 0， 而且是恒等式，也就是不管 t 多少都是永远0。那唯一的可能就是这两个系数都要是0，你才能够得到这个恒等式。那这两个系数分别就是 big A equals 0 and big B equals 0。And the big A, big B can be evaluated by the substitution. So this is the result. Big A equals 1 over omega c squared TP squared plus G minus L. It is 0. Big B equals gamma times A0 squared minus 2 over omega c squared TP squared. It's also 0. So we have two algebraic equations. And from these two algebraic equations, we can solve the two unknowns, A0 and the TP. So you see, this is a transformation from differential equation to algebraic equations. Of course, the later one is easier. 微分方程不好解 ，in general 不好解，尤其是非线性。但是经过转换之后，它已经变成代数方程了。代数方程就好解所以你把未知函数简化成 已知函数的2个未知系数去找解。Things could be much easier. Okay. But be careful. G is the constant gain. It is not an independent coefficient. It's actually a function of A0. Remember, the governing equation of constant gain is small signal gain G0 over 1 plus average power over saturation power. G0 and the PG are 2 given constants. You have to know them in advance. Okay? But the P average is not. Average power is not a given constant. You have to calculate. And the average power, according to our previous slide here, right? 2A0 squared TP over TR. So it's a matter of unknown A0 and unknown TP, their product. Okay? So actually, G is a function of unknown A0. 所以你不能把它看作一个会给你的常数哦，这个也是一个 function of 未知数 A0 所以这个要放进去考虑。Okay, the other thing is how do you solve the system of algebraic equations? What have you learned before? Maybe in the high school years. How did you solve the system of 2 combined algebraic equations? You probably learned 2 methods. One is, I don't know how to translate, maybe in Mandarin it's 代入消去法。另外一个叫什么？加减消去法。What is 代入消去法？ You have 2 unknowns, right? Just eliminate one of them, representing maybe unknown 2 in terms of some equation of unknown 1. Then you can have a single solution, a single equation of single unknown, right? That's the central idea of 代入消去法. So here we did the same thing. We have 2 unknowns, A0 and the TP, but could we represent TP in terms of A0? If we can do that, the 2 algebraic equations can be simplified to a single algebraic equation with single unknown A0. Okay? But what's the relation between A0 and the TP? It comes from equation 2, right? From equation 2, gamma times A0 squared has to be equal to 2 over omega c squared TP squared. So the relation is already there. You can represent TP in terms of A0. And if you do so, average power is a function of single variable A0 only. No longer with TP explicitly. This is the idea that you have known before. Okay? Any question? But before we jump into the solution of A0, then solution to TP, let's pay some attention to the insight of the physical meanings of the 2 equations. For example, equation 1, if you review equation 1, what does it mean? This is equation 1. If you don't pay attention, it's simply a mathematical equation. Does not make sense for you. But can you give equation 1 some physical interpretation? The answer could be like this. Net gain, G sub t, when the laser power is 0, should be G minus L, right? G is the constant gain. L is the linear loss. Total linear loss. Okay, but our total loss is not a constant loss, but a loss then with some self-amplitude modulation term. But it will disappear when your laser power is 0, like the pulse tail, the 2 pulse wings. 在2个 pulse wing 或者更远的地方 P of t is almost 0. If P of t is 0, then SAM term does not occur. Okay? So your total loss is only linear loss, small L only. Sorry. Your gain has no dynamics, so no matter it's pulse tail or pulse peak, it's always constant gain, G. So G minus L means the net gain when there is no laser power. Okay? And according to equation 1, G minus L has to be this number. Okay? Go back to equation 1. G is here, L is here. G minus L is always equal to shifting this term to the right-hand side of equality. You got minus 1 over omega CTP parenthesis square, right? And this number is always negative, as you can see, because of the square. Okay? So it means G minus L is always 0. But G minus L means the net gain seen by the pulse wings. So that means pulse wings always see net loss or negative net gain. Okay? And it also means the pulse is self-sustaining after its formation. It's a very important characteristics. Think about here. If both pulse wings see net loss, whenever there is some noise, it will not get amplified, then eventually disturb your pulse. It will be attenuated by this net loss. So it's good for self-sustaining, stabilizing your pulse trend after its formation. Okay? 好，所以这个 governing equation 其实已经告诉我们，这个机制有先不管脉冲形成的过程，脉冲一旦形成之后 ，after its formation， 这个机制会自动帮你稳住这个 pulse train， 因为难免会有 noise 跑出来 ，noise 出现的位置通常影响最大的就是在 pulse wings，noise 也会出现在 pulse peak，but pulse peak has a very strong power。Noise is relatively unimportant, right? But for pulse wings, they are important. If during the pulse wings they see the net gain, then a small noise can get amplified again and again. Eventually, your pulse train will be destroyed. But here, the net loss guarantees this noise will not get amplified. They will be attenuated. Okay, it's already predicted by the formula. And if you check equation 2, you can see your peak power by formula is A0 squared, and it's proportional to 1 over Tp squared. Total energy is proportional to 1 over Tp, and so forth. So it means peak power and the pulse energy depend on pulse width. They are not two independent variables. 意思说，我在这个 passive Molag laser 里面呢，我的 solution 一定是 second hyperbolic function， 而且它的振幅跟宽度不是独立可以变的。这边告诉你，当你把脉冲变窄的时候，你的 peak power 一定会增加，你的 pulse energy 也一定会增加。一个是平方反比，一个是一次方反比，所以你不可以任意的把我的 pulse 压缩一倍，然后我的 peak power 呢没有平方增加，这不可能是 solution， guaranteed by equation 2。Okay, so that's the second interpretation about our algebra equation. Any question? Okay, this could be a very important page in this lesson. Steady state. Gain equals average loss. That's the conclusion. But let's see why is that. If you combine equations 1 and 2, you will arrive at a nonlinear equation of unknown A0. Roughly speaking, it's h of A0, a function of A0, equals f of A0, another function of A0. And both are nonlinear functions of A0. 所以简单的说，你把 equations 1 and 2合并起来，你用所谓的代入消去法，你会得到某一个非线性函数要等于另外一个非线性函数。这两个都是 A0 的函数。这两个函数相等，就代表这两个函数的 curve 的交点 ，the crossing point would be the solution. The crossing point determines A0. What is the solution A0? And if you know A0, you can calculate TP. You can know everything. Okay, that's the idea. But the question is, could you give physical interpretations for h and f, the two nonlinear functions? Okay. Let's check the figure. This is the driving pulse, the power of the driving pulse, P of t. This is the peak power, okay? According to our model, peak power is equal to A0 squared. A0 is the amplitude of the unknown variable, unknown second hyperbolic pulse, okay? And the blue curve is the total loss curve. Big L, small l, which is LC plus L0, okay, minus self-amplitude modulation term, gamma coefficient times the driving laser power, P of t. Okay, so this is the driving pulse. The blue one is the total loss curve. It's fast saturable absorber, so you can see the curve responds to the driving power immediately, as you have known. Then what is the meaning of the first nonlinear function, h of A0? H of A0 equals delta over 2, where delta equals L minus L minima. Okay, so let's see here. This is L. Okay, the loss when there is no power, the loss is L. L minima is the minima loss. That means the loss corresponds to the peak, laser peak, right? So it's here. L minima is here. The difference, this is the difference. L minus L minima is the difference. It's specified by a big delta, okay? And the big delta is the so-called loss saturation depth, right? 这一段的距离就是所谓的 saturation depth of the absorber, right? 没有 pulse， 我的 loss 这么高，最强的 peak 出现的时候，我 loss 这么低，这个之间的差距就是所谓的 loss saturation depth. And mathematically, L minus L minima equals gamma times A0 squared. Is it okay? What is L? What is L of t? Your total loss is this one. What is L minima? When P of t equals peak power, right? So L minus L minima, L 跟 L cancel， 剩下来的就是 gamma 乘上什么 peak power, okay? And we also know peak power equals A0 squared, so this is the final result. Delta equals gamma constant. You have to know gamma coefficient in advance times A0 squared. So basically, h is proportional to A0 squared, a quadratic function of A0. It's a parabolic curve. Okay? So that's the meaning of h function. The second function is f of A0. f of A0 is L minus G. L is the loss when there is no laser power. G is your constant gain, which is denoted by the red dashed line here. Okay? And this is the difference. It's f of A0. Okay. And the G is not the given constant. It's related to average power, and the average power is proportional to A0. So G is also a nonlinear function of A0. But it's not cubic, it's not quadratic, it's not linear because of the functional. 因为这个函数形式的关系，你这里有一次方的 a0，可是它在分母又在一个加减的 term 里面，所以这不是一个简单的正比或平方或三次方的 a0 函数 ，but it's a nonlinear function of a0, and you got the f function. The meaning, the difference is here. It means the net loss seen by the pulse wings. Okay. This is pulse wing, right? The difference, L minus G, if it is positive, that means loss is bigger than your gain. It means net loss. And the f function only refers to the net loss of seen by the pulse wings. It does not apply for the pulse peak, right? Because for pulse peak, the total loss is no longer L, it's L minima. So f function can be interpreted as net loss seen by the pulse wings. Okay, any question to this point? I just give you interpretation for the two nonlinear functions, h function and the f function. One is about, h is about loss saturation. And precisely speaking, h function means 1/2, right? Delta over 2. So 1/2 of delta, and the delta is loss saturation depth. That's the physical meaning of h function. And the physical meaning of f function is net loss seen by the pulse wings. And the steady state solution requires h equals f. H equals f. So roughly speaking, this length should be 1/2 of this length. Or roughly speaking, the red dashed line has to be cut through about the middle between the blue curve. Is it okay for you? 这两个相等，意思就是照字面来讲，这个的长度必须是这个的一半。那也就是这一条红色的水平线，是不是大概要砍在这个蓝色 curve 深度方向大概中间的位置？这个条件才会满足。Okay, so whenever this level is away from the middle, it's not solution. You have to adjust the red one and the blue one. Remember, both curves will change with A0, right? When A0 changes, your H curve changes quadratically. When A0 changes, your F curve will change according to this nonlinear relation. 所以你的 A0 改变，就是你的 pulse peak 改变，事实上也就代表 pulse width 在改变。这两个 curve 都会变的，一直要变到刚好切在一半，才会是你的 solution。其他的状况都不是 solution。Okay. So graphically, that's the meaning of the algebraic equation. And if this figure applies, you can see a net gain window around the pulse peak, right? Within this temporal window, your gain, which is the red dashed curve, is higher than the loss, total loss, your blue curve. So this is a net gain window. Window means the range is not infinite. There is a finite range. And this range is around the post-peak. And that's the post-shortening effect we need, right? If you have a net gain window around the post-peak, it means if you consider both gain and the loss together, your post-peak will be amplified most. Because here, your gain is much larger than your loss. But your post-wins will get attenuated because your loss is larger than the gain. Then you see you have a post-shortening effect due to the interplay between the loss and the gain. It's not due to any external modulator. Okay? In active mode locking, we need external modulator, but here we don't. Just carefully play with the gain dynamics and the loss dynamics. You can create a temporal window, a net gain window for post-shortening. Is it okay for you? Okay, then if you use H equals F by simple rearrangement, H equals here, delta over 2, delta equals L minus L minima, F equals L minus G, just simple substitution. You can arrive at this result. G equals L plus L minima over 2. They are the same. And this relation corresponds to this sentence. Gain equals average loss, right? G is the gain, constant gain. L plus L minima, L is here. L minima is here. The summation divided by 2 should be the average loss. Your loss is not a constant. It varies with time. But in average, the average value is about maxima plus minima over 2. So the right-hand side means the average loss. The left-hand side means gain. So when gain equals average loss, steady state is reached. Okay? You can have the solution. Okay, any question?好，那我们想想看哈，这个图其实包含很多 information， 我们待会会持续用到哈。For example， 我刚刚说我的 pulse 改变，这两个 curve 都会改，我们看看怎么改。我的 pulse 如果把 peak power 往上增加，那我前面说 peak power 跟 pulse width 不是独立的。当我的 peak power 往上增，我的 pulse width 就必定要缩减，不然就违反 equation 2， 这是 equation 2强加给我们的条件啊。如果我的 peak power 上升，我的 pulse width 变窄，那么 for example 蓝色的 curve 会怎么动？很简单，这个 loss 是来自这个 power 的 saturation。So if you have a bigger peak power, that means you have deeper minima loss, stronger loss saturation for sure, right? 好，所以如果红色的不动，蓝色的变深，你切到的位置就不是 1/2. It's not the steady state solution. But interestingly, the red curve will change with peak power as well. How does it change? When your peak power is stronger, A0 is stronger, check the formula about G. Average power is proportional to A0, so stronger average power, bigger denominator, smaller G. And actually it's natural. If you have stronger peak power, that means you have larger average power. And your gain saturation is even stronger. You have a smaller gain. So the red dashed line will be lower. Okay? Then it's again possible, right? your blue curve is steeper, but your red curve is also lower. So maybe you can cut through the middle. 这两个不是独立的，它会一起动。OK， 但是就是要动到刚刚好 ，gain 等于 average loss 才会是你的 steady state。OK， 你离开那个这个1/2的地方，它就不是 steady state solution。Okay, so think about this picture. We will use this figure later to analyze some characteristics.